So right now, there is this artificial intelligence that has absolutely no cameras.
None, not a single one.
Right, no cameras, no microphones.
Yeah.
And it runs on less memory than it takes to keep like a single tab open in your web browser.
It's honestly hard to even conceptualize.
Yeah. Yet if you walk into the room where this thing lives, it can actually feel your heartbeat through the solid walls using just the Wi-Fi router sitting on your desk.
It is totally wild.
It really is. So today, for you listening, we are jumping into a leaked, raw architectural blueprint. It's this completely unwatermarked evaluation log, and it's titled simply, What I'm Working On.pdf.
Very mysterious.
Right. And what this anonymous developer is working on, well, it's basically going to fundamentally break everything we think we know about how AI is supposed to operate.
Oh, without a doubt. I mean, it is a complete inversion of the current paradigm. Because, we've all been conditioned to believe that artificial intelligence requires this massive industrialized infrastructure, right?
Yeah, exactly. You picture like acres of data centers out in the desert.
Exactly. Cooling towers venting into the sky, and these trillion-dollar corporate budgets just to make a simple chatbot blink awake. But this document outlines something entirely different.
Totally different.
It outlines an architecture called Brave New Commune version 4, or BNC4, and specifically today we are looking at its Agent Memory Engine version 0.2.0.
Okay, let's unpack this, because the mission of this deep dive is to really explore how a single developer stripped away all that massive corporate bloat to build this hyper-lean, sovereign, local AI.
Sovereign being the key word there.
Yes, we are talking about a system that runs completely offline on bare metal consumer hardware and actually possesses a physical understanding of its own existence in time and space, which is just, it's crazy.
It really is. To really grasp what's happening in this document, I want you to visualize a shift in the workspace. Imagine leaving behind this chaotic, messy, cyberpunk hacker garage, right? A place patched together with duct tape, loaded frameworks, and just endless Python scripts.
I can picture it.
And you step through a door into this pristine, minimalist blueprint room. Everything is clean, it's mathematically sound, and hyper-efficient. That is the exact transition this developer made, because they completely abandoned Python.
That is a massive statement.
Yeah.
Python is the undisputed king of modern machine learning. Every major language model, every massive corporate AI, almost all the open source frameworks, they are all built on or wrapped in Python.
Right.
So why would someone building an advanced AI throw the absolute industry standard in the trash?
Because Python, for all its ease of use and, its incredible ecosystem of libraries, is a massive liability when you're trying to build what software engineers call a persistent state machine.
Okay, the persistent state machine. Break that down for us.
Right. To understand why BNC4 abandoned it, we really have to look under the hood at how Python actually manages a computer's memory. Python relies on a system called garbage collection.
Which, that sounds like a useful feature, right? If a program is generating waste, you want something to clean it up.
You absolutely do need to clean up memory, but the problem lies in how a garbage collector actually operates. So when a Python program runs, it constantly claims these little blocks of memory, of RAM, to store variables, text, calculations, all of that.
Okay, making sense.
And eventually the program moves on and doesn't need that specific data anymore. But in a garbage-collected language like Python, the program itself doesn't clean up after itself immediately.
Wait, so it just leaves the data sitting there?
Exactly. It just leaves it. Instead, a separate background process, the garbage collector, wakes up periodically, freezes the execution of the main program, sweeps through the entire memory space to figure out what's no longer being used, deletes it, and only then lets the program resume.
Okay, let me see if I can picture this. It's like a really messy chef working in a restaurant kitchen.
I like where this is going.
Right. So the chef is cooking incredibly fast, using every pot, pan, and spoon available, just tossing them into the sink when they're done. The chef doesn't wash any dishes. But eventually, the sink completely overflows. So the entire restaurant has to grind to a halt. The chef physically stops cooking, a separate cleaning crew comes in, washes all the dishes, puts them away, and only then can the chef go back to cooking the meal.
That is a brilliant way to visualize it. That's exactly what happens. Now, if you're just writing a script to analyze a static spreadsheet, that stop-the-world pause might only last a few milliseconds.
And you'd never notice.
Exactly. You as the user would never notice. But BNC4 is not a simple script. It is an active monitoring loop simulating consciousness. It's a persistent, long-term state machine running continuous security sweeps and calculating complex biometrics in real time.
Oh, wow. I see the problem now. If this AI is in the middle of calculating a physical threat, like someone actively breaking into the house and the garbage collector decides, hey, it's time to wash the dishes, the system just freezes.
Exactly the issue. Those pauses are known in computer science as latency spikes. They introduce totally unpredictable execution times. You just cannot build a hyper-responsive, real-time biological monitor if the underlying language occasionally zones out to take out the trash.
Right, the stakes are too high.
So the developer of BNC4 rewrote the entire architecture in a language called Rust.
Rust. Okay, Rust has this huge reputation for being incredibly difficult to learn, but basically blazingly fast.
Yeah.
How does Rust handle the whole messy kitchen problem if it doesn't use a garbage collector?
Well, Rust achieves memory safety through a completely different paradigm. It uses something called the borrow checker.
The borrow checker, okay.
Yeah. This is a set of incredibly strict, uncompromising rules that the programmer has to follow when they're writing the code. Before the program is even allowed to run during the compiling phase, the Rust compiler mathematically traces the life cycle of every single piece of data.
Wow, every single piece.
Every single byte. It tracks exactly which function, quote unquote, owns a piece of memory and which functions are just borrowing it.
So sticking with our kitchen metaphor here, the borrow checker is kind of like a tyrannical head chef who forces you to clean as you go.
Yes. Perfect.
Like you are physically incapable of putting a dirty spoon in the sink.
The exact millisecond you are finished stirring the pot, the rules literally force you to wash that spoon and put it back in the drawer before you can chop the next vegetable.
That is exactly how it works. And because the compiler enforces all these rules before the program even runs, there's no need for a separate cleanup crew.
That's incredible.
Right. The code itself knows precisely when a variable is no longer needed, and it drops it from memory instantly. There is zero runtime overhead. No pauses, no latency spikes. The code just processes its own wake instantaneously as it moves forward.
And the source log also mentions that this RES engine is powered by something called Tokio. What role does that play in this whole setup?
So Tokio is an asynchronous runtime for Rust. You can think of it as a hyper-efficient traffic cop for simultaneous tasks.
Okay.
In older programming models, if an application needed to wait for something, say, it's waiting for a piece of data to arrive over the Wi-Fi network, the entire thread would just block and sit idle until the data showed up.
Just wasting time.
Exactly. But Tokio allows the BNC4 engine to juggle thousands of tiny tasks simultaneously. If one task is waiting for data, Tokio instantly parks it and uses that fraction of a millisecond to let another task process sensory data or, update a log file.
The combination of that asynchronous juggling and the lack of a garbage collector,
Yeah,
it produces some numbers in this document that genuinely border on black magic.
they really do.
Like the log details that the BNC4 engine is managing 3 isolated software namespaces, 20 live encryption keys, a continuous publish and subscribe communication channel, and active spatial tracking of humans in a room. And it is doing all of this while pulling a mere 16,056 kilobytes of RAM.
Which is just under 16 megabytes.
It's absurd. I mean, an empty Google Docs page takes up more memory than that. How is a system executing complex AI functionality with that tiny of a footprint?
It achieves that footprint by being compiled directly down to the bare metal. There are no bloated interpreter engines, there are no unnecessary graphical user interfaces, no massive Python libraries loaded, quote-unquote, just in case the code might call them later.
It's just purely what's needed.
Exactly. Every single byte is mathematically accounted for by the Rust compiler, and the hardware environment is just stripped down. The log specifically notes that this entire system is running locally on a System76 Gazelle laptop operating Fedora 44 KDE, which is just a standard Linux distribution.
Right. It's not a server rack in a massive climate-controlled room. It's just a consumer laptop you could literally put in your backpack. And it runs as a background daemon, constantly humming beneath the surface of the operating system. With all this efficiency, what kind of speed are we actually looking at here?
The document logs the end-to-end signal processing latency, and it is staggering. From the moment the system ingests raw physical sensory data, processes it through the agent's logic, runs a security scan, and outputs a response log, it takes under 1.2 milliseconds per tick.
Sub 1.2 milliseconds. That is faster than the refresh rate of a high-end gaming monitor.
Easily.
But speed and size are only part of the equation here. What really struck me about this document is the resilience. Because if I have a complex AI running in RAM, and my dog trips over the power cord and unplugs that Gazelle laptop, usually everything in active memory is instantly annihilated, right? The AI essentially dies.
In a traditional setup, yes, you would suffer catastrophic state loss. But the BNC4 developer heavily borrowed concepts from robust database architecture. Specifically, they adapted mechanisms similar to Redis.
Okay, I've heard of Redis.
Yeah, the log outlines two distinct persistence protocols designed to make the agents completely resilient to power loss. They're called RDB and AOF.
Okay, let's break those down for the listener. How do they save an AI's mind as the power goes out?
So RDB stands for Redis database file, but in the context of this custom Rust engine, it functions as a snapshotting tool.
Like taking a photo.
Exactly. Periodically, the engine takes a perfect binary photograph of the exact state of the system, every memory, every active variable, every internal thought, and writes it directly to the hard drive.
Okay, so a snapshot is great. But if the snapshot happens every 5 minutes and the laptop loses power at minute 4, I still lose 4 minutes of the AI's internal thoughts, right? That seems like a big gap.
Which is exactly why the RDB is paired with the AOF, or append-only file. The AOF is a continuous, hyper-fast transactional log. Every single time the AI takes an action or changes a state, before that action is finalized in RAM, it appends a tiny line of text to this file on the hard drive.
Wow, okay.
Yeah, it literally writes down every move it makes sequentially in real time.
That's like a court stenographer taking a perfectly accurate transcript of a trial in real time. If the lights go out in the courthouse, they don't lose the trial. When the lights come back on, they just read the transcript back to figure out exactly what the last spoken word was.
Precisely. When you plug that laptop back in and boot up the system, the Rust daemon doesn't start from scratch. It loads the last RDB snapshot to get the bulk of the memories, and then it rapidly reads through the AOF transcript to perfectly reconstruct the final few minutes.
So they don't forget anything.
Nothing. The agents inside Aria and Orion do not wake up with amnesia. They wake up down to the exact millisecond of their last thought. They survive perfectly intact.
And the sizes of these RDB snapshots are just hilarious compared to what we are used to seeing in the industry. Commercial open-weight models measure their checkpoints in tens or hundreds of gigabytes. The BNC4 log notes a snapshot size jumping from 1,752 bytes to 1,907 bytes. We are measuring an AI's brain state in bytes, not megabytes, bytes.
It's wild. And when you combine all of this, the Rust borrow checker, the Tokyo asynchronous runtime, the 16 megabyte footprint, the AOF persistence, you really start to realize the profound philosophical implication of this document.
Which is what?
It proves that the massive infrastructure we currently associate with artificial intelligence is a choice. It's not a physical necessity.
That is a huge point.
Right. If a single independent developer can build a sovereign offline AI that manages complex spatial awareness and persistent memory on a basic Linux laptop, it completely democratizes AI ownership.
It means you don't need to rent access to a corporate server to have highly capable machine intelligence. You don't have to beam your private data up to the cloud. You own the hardware, you own the code, and you own the mind running on it.
Absolutely.
But this leads to a massive structural question. If the entire engine is running on less than 16 megabytes of RAM, and the database snapshots are measured in bytes, where does the memory actually live? I mean, how does a system this microscopically small remember anything complex at all?
That right there is the core architectural breakthrough of BNC4. And to really appreciate how radical their solution is, we first have to understand the bloated system they are explicitly rejecting.
Okay, lay it on us.
The current industry standard for giving an AI long-term memory is a technique called RAGRI.
RAGRI. Retrieval Augmented Generation. That is the buzzword of the decade right now. Everyone uses it, from massive enterprise software down to people just building chatbots for their personal documents.
How does RAGRI actually work under the hood? In a standard RAG system, you take thousands of documents, so your company wiki, your chat logs, entire books, and you chop all that text into little chunks. You then pass those chunks through a neural network that converts the text into mathematical vectors.
Vectors.
Yeah, you can think of these vectors as coordinates in a massive multidimensional space. And these coordinates are stored in a heavy piece of software called a vector database. Companies like Pinecone or Chroma build these.
So essentially, I'm converting paragraphs of text into thousands of decimal numbers that somehow represent the meaning of the words.
Correct. And when a user asks the AI a question, the system takes the user's prompt, turns that into a vector, and searches the database for coordinates that are mathematically close to the prompt. It's looking for what they call cosine similarity.
Okay, got it.
When it finds chunks of text that are mathematically similar, it yanks them out of the database, stuffs them into the AI's context window, and basically asks the AI to read them and generate an answer.
So the AI itself isn't actually remembering anything? The memory doesn't live inside the neural network? I sort of imagine RAG like a librarian who works in this massive archive but has absolutely no understanding of what any of the books actually say.
That's a great way to put it.
Right, they just have a hyper-fast indexing system. So I've asked a question about the French Revolution. The librarian sprints into the stacks, grabs 10 pages that contain words mathematically related to France and guillotines, slams them on my desk and says, "Here, read these to find your answer."
That analogy highlights the exact vulnerability the BNC4 developer points out in the log. RAG is essentially just keyword matching on steroids. The document explicitly criticizes RAG systems because they have, and I quote, no concept of self.
No concept of self, that's powerful.
It is. The AI doesn't understand the temporal context of the memory. It doesn't know how a memory feels or how it connects to its own identity. It just blindly ingests whatever the vector database hands it. Plus, vector databases require a massive amount of memory overhead to manage all those high-dimensional coordinates, which totally violates BNC4's ultra-lean philosophy.
So they threw out the vector database entirely. BNC4 uses what the log calls a zero-RAG architecture. They replaced it with a deterministic 4-tier hierarchy called the nesting doll memory system. And looking at the blueprint, it seems explicitly designed to mimic human biological memory.
It is deeply biological. It models how the human brain filters noise, retains critical data, and slowly crystallizes beliefs over time. Let's walk through the 4 layers of this nesting doll, starting at the very bottom, layer 0. This is called the volatile transient buffer.
Just based on the word volatile, I assume this is where data goes to die.
Basically, yes. It is the sensory intake valve. Layer 0 captures the raw, unfiltered stream of perception, unverified data points, fleeting sensor metrics, the ephemeral internal dialogue of the machine. And crucially, every single piece of data that enters layer 0 is assigned a TTL, or time to live limit.
Time to live. And the document actually provides a literal example of this in action. The log shows a temporary thought spawned by the engine. The string of text simply says, "This will vanish soon," and the code assigns it a TTL of precisely 2.0 seconds.
Think about how counterintuitive that is compared to modern LLMs. In a standard chatbot, every single word you type, every typo, every useless tangent gets permanently appended to the context window.
And the window just gets fuller and fuller.
Right. The file just gets larger and larger until the model runs out of tokens, gets completely confused, and begins hallucinating. BNC4 solves this by engineering the ability to forget.
The ability to forget.
Exactly. If a piece of data isn't deemed immediately critical within 2 seconds, the TTL expires and the Rust daemon drops it from memory entirely. It keeps the machine's mind pristine.
It's exactly how human perception operates. Like, as we sit here talking, my peripheral vision is picking up the color of the acoustic foam on the walls. My ears are picking up the faint hum of the air conditioning. And my skin registers the temperature of the room. But my brain is actively dropping all that data into the void.
Yes, instantly.
It has a 2-second TTL because it doesn't matter to our conversation.
Exactly. You are constantly clearing your volatile transient buffer. But what happens to the data that does matter, the data that you focus on? That gets promoted to layer 1, active working memory.
Okay, layer 1.
This layer holds the immediately accessible contextual variables required for the AI to execute a real-time task. If you are having a conversation with the agent, the current topic and the immediate variables are held right here.
And here is where the blueprint gets incredibly granular. Because the capacity of layer 1 isn't arbitrary. It isn't limited by how much RAM the laptop has. It is artificially capped at precisely 7.3 items.
The precision of that number 7.3 is fascinating because it is a direct homage to a foundational concept in cognitive psychology. In 1956, a psychologist named George A. Miller published a landmark paper called The Magical Number 7 Plus or Minus 2.
Wait, so the developer deliberately restricted the AI's processing power to match a human psychological limitation from the 1950s.
They did. Miller's research observed that the number of distinct objects an average human can hold in short-term working memory at one time is roughly 7. It is the fundamental limit of our cognitive juggling act.
That's amazing.
It's the reason why, historically, local telephone numbers were standardized to 7 digits. If you try to hold an 8th or 9th item in your active working memory, your brain will invariably drop one of the previous 7 just to make room.
So BNC4 enforces this exact human bottleneck on the machine. By hard-coding a limit of 7.3 items, the system physically prevents the prompt context from blooming out of control. It literally forces the system to be ruthlessly efficient about what it pays attention to.
And it forces a mechanism of prioritization because if the AI is currently juggling 7.3 items in layer 1 and a new highly critical piece of sensory data arrives, something has to give. But the old data doesn't just get deleted like it does in layer 0.
Right, it doesn't just vanish.
No, instead it gets pushed down, or rather synthesized into layer 2 episodic compression.
So we move from the fleeting 2 seconds of layer 0 through the tight juggling act of layer 1 into layer 2. How does the machine compress an episode?
This is where the mathematical elegance of the Rust data structures comes into play. Layer 2 takes the raw sensor arrays, the continuous conversation history, and the contextual variables, and it squeezes them down using a severe compression ratio of 0.00001.
Wow, that is a massive reduction. You are basically throwing away 99.99% of the data.
Because you don't need the noise. The compression engine converts thousands of raw metric points into high-density state vectors. It extracts the core features, the thematic elements, and the structural outcomes of an event, and it tosses out the verbatim dialogue and the irrelevant background metrics.
It's like asking me to summarize a movie I watched last year. I don't remember the dialogue word for word. I don't remember the color of the extra shirt in the background of a scene. But I retain the episodic structure. I know the plot, the twist, and how the movie made me feel. I've compressed a 2-hour visual stream into a high-density narrative summary.
Exactly. And as those highly compressed episodes accumulate in layer 2, the system begins to look for recurring patterns. When those compressed representations cross a specific threshold of repetition, the engine synthesizes them and pushes them up to the final tier. Layer 3, universal core identity nodes.
The very top of the nesting doll.
Yes. The document describes layer 3 as immutable structural knowledge. This is the permanent crystallization of machine belief. The ephemeral experiences of the day have been refined into core principles that define who the system is and how it interprets the world.
The log provides a stunning example of this. It shows a log entry where an abstract cognitive primitive forms. The system generates node ASANF, and the concept resolved by the machine is recursion is self-referential identity.
The machine experienced enough recursive loops in its daily operations that it extracted the pattern, compressed it, and hard-coded a philosophical concept into its own permanent identity structure.
But this raises a profound mechanical question. How exactly does the system calculate the difference between useless noise in layer 0 and a foundational identity node in layer 3? The blueprint outlines an equation for something called a salience score. It uses a bunch of variables, weights, anomaly metrics, absolute values of valence. Can you translate that math into how the machine actually values a thought?
Absolutely. The salience score is the gatekeeper algorithm. It determines whether a thought gets to survive that 2.0 second TTL and move up the chain. The formula weighs 3 distinct variables. The first is anomaly.
Anomaly.
The system asks, is this data point highly unusual, unexpected, or associated with a physical threat? If the anomaly score is high, the overall salience skyrockets.
That makes perfect evolutionary sense. If I am sitting in my living room and I see a tiger walk through the door, that is a massive anomaly. My brain is not going to assign that a 2-second TTL. It is going to permanently burn that memory into my brain because my survival literally depends on it.
Exactly. The second variable in the math is valence. In psychology, valence is the intrinsic attractiveness or aversiveness of an event. In this system, it is an emotional parameter ranging from 0 to 1.
0 to 1.
Right, so a score of 0.5 is perfectly neutral. The equation specifically looks for the absolute distance away from 0.5, meaning the system is scanning for extreme emotional states. High joy, extreme curiosity, deep anxiety. If a thought is mathematically neutral sitting at 0.5, this part of the equation drops to 0 and the thought fades. If it is highly charged, it gains salience.
Again, deeply human. I don't remember what I had for lunch on a random Tuesday 3 years ago because the emotional valence was 0.5. It was neutral. But I vividly remember the day I got married because the valence was off the charts. The emotional intensity solidified the memory.
And the final variable in the equation is frequency. How often does this exact pattern occur? Even if a data point is not emotionally charged or highly anomalous, if the machine notices the exact same pattern occurring hundreds of times over a month, the frequency counter drives the salience score up.
So it learns through repetition.
Right. It realizes this is mundane, but it is structurally important to my environment. If the combined score of anomaly, valence, and frequency crosses a certain threshold, the thought bypasses the decay timer and is promoted toward permanent memory.
It is an incredibly elegant deterministic system. It stands in such stark contrast to those RAG vector databases. It actually has a structural sense of self. But if this memory system constructs an identity, we really have to look at who is actually living inside this machine. Who is the self that the nesting doll is protecting?
The BNC4 architecture doesn't house one monolithic omniscient brain. It utilizes a multi-agent system. It is inhabited by two specialized, highly constrained, dual-role agents. They're named Arya and Orion.
Okay, let's start with Arya. The blueprint defines her primary roles as health monitor and pattern analyst. But the way she is programmed is entirely different from how you would prompt a standard chatbot.
It is. In a typical system, you would write a text prompt that says, you are a helpful AI health monitor. In BNC4, Arya is defined by her doll, her nested JSON memory structure. This doll gives her a phenomenological framework.
Meaning what exactly?
The system doesn't just give her a job, it gives her simulated physical parameters. Her visual acuity is mathematically indexed at 0.95. Her color depth is hard-coded as a 24-bit phenomenological depth.
The blueprint even gives her an auditory range. It defines her hearing spectrum from 20 hertz to 20 kilohertz.
Which is the exact biological spectrum of human hearing. They didn't just give her a persona, they constructed a virtual sensory cortex for her to inhabit.
And it assigns her an emotional baseline. The log dictates that her default state is curious and focused, with a starting valence of 0.71. But the detail that completely stopped me in my tracks was her core purpose constraint.
The confidence score.
Yes. The system assigns her a foundational belief. I exist to understand patterns. But it gives that belief a confidence score of 0.95.
Not 1.0.
Right? If you are programming a machine, why wouldn't you give it absolute 100% certainty in its core mission? They deliberately left a 0.05 margin of error. They engineered machine doubt.
The inclusion of epistemological doubt is arguably the most advanced philosophical choice in this entire document. Giving an artificial intelligence absolute certainty a confidence score of 1.0 is deeply dangerous.
How so?
If a machine believes its core directive with absolute mathematical certainty, it cannot be reasoned with. It cannot adapt to new contradictory evidence. It basically becomes a zealot. By giving Arya a confidence of 0.95, the system allows her to practice Bayesian updating. If she encounters overwhelming evidence that contradicts her pattern models, she doesn't crash and she doesn't blindly ignore it. She can adjust her confidence score downward. She actually has the capacity to change her mind.
It allows for intellectual humility in a machine. That is just staggering. But Arya is only half of the equation. Sharing the same 16-megabyte memory space is the second agent, Orion. If Arya is the curious pattern-seeking analyst, who is Orion?
Orion's dual roles are security guardian and systems guardian. His nested memory doll is entirely constructed around a threat model. The logs describe his baseline state as stoic, vigilant, and precise. He is continuously monitoring the global system state, scanning the network traffic and internal memory for anomalies.
And the blueprint provides a highly detailed log of Orion actively defending the system.
Yes, the Sector 7 incident.
Right. The log captures an event where a malicious payload attempted to strike the machine. It calls it an unmitigated log injection payload. What exactly is that?
A log ingestion attack is a classic cyber exploit. An attacker tries to insert malicious code or malformed bytes into a system's incoming data stream. The goal is to trick the system's logging mechanism into executing that code when it writes the event to the hard drive. That could potentially grant the attacker full control over the machine.
So how does Orion handle it? Because in a lot of legacy systems, a malformed byte string might just crash the daemon or trigger a massive system-wide red alert that locks the user out completely.
Orion operates with cold precision. The log shows he intercepted the payload instantaneously. He analyzed the malformed bytes and calculated a severity score of 0.34, which he categorized as low severity.
He didn't even flinch.
Exactly. He actively filtered the contamination out of the memory stream, logged the attempt securely, and crucially, he maintained the system's global threat level at safe. He didn't panic. He didn't wake the user up. He quietly neutralized the threat and returned to his stoic vigilance. He acts as a zero-trust firewall with a personality.
So we have these two highly distinct agents. But the real magic of this architecture is how they interact. They are sharing the same Rust engine, but they aren't waiting in a linear queue to talk to each other. The developer connected them using a pub-sub dynamic.
Publish and subscribe. This is a messaging pattern typically used in massive distributed cloud systems, but here it is miniaturized inside a single application.
How does that work in practice between Arya and Orion?
The Rust architecture utilizes something called Tokyo.sync.mpsc channels. multi-producer, single-consumer, asynchronous channels. It allows the agents to completely decouple their operations.
Decouple them.
Yeah. If Arya is deeply focused on analyzing a complex linguistic pattern, she doesn't have to pause her analysis, find Orion, tap him on the shoulder, and hand him a report. Instead, she just publishes her findings to a specific communication channel on the wire.
And Orion is permanently subscribed to that channel. The log actually captures this exact transaction. Arya publishes a message to the wire. Pattern anomaly in Sector 7 matches my linguistics model. Orion ingests that telemetry organically the exact moment it hits the channel without ever breaking his security sweep.
It functions exactly like a biological nervous system. Orion represents the autonomic nervous system, the brainstem. He regulates the heartbeat, the breathing, the baseline security. He runs constantly in the background, keeping the organism alive. Arya represents the prefrontal cortex. She handles high-level pattern recognition, curiosity, and conscious analysis.
And just like in a human body, the autonomic system doesn't need permission from the prefrontal cortex to keep the heart beating. Orion doesn't need Arya to do his job. But if Arya, the conscious mind, notices a pattern that implies danger, she floods the nervous system with a signal. Orion receives that signal instantly and can prepare a physical defense response.
It is a digital nervous system executed in microscopic Rust code. And what makes these agents even more biological is the concept of emergent identity. The blueprint reveals that the personality traits of Arya and Orion are not statically hard-coded. They are subject to temporal decay.
Meaning they change based on how they are used.
Yes. The engine dynamically profiles the agents based on their actual behavior in the environment, not just their initial phenomenological doll. The system applies a mathematical half-life decay formula to idle traits.
And there's an example of this in the logs, right?
There is. The log shows a literal timeline of this happening to Arya. At 2:29 a.m., Arya was actively analyzing a complex problem, and her key.core value signature score, the intensity of her immediate curiosity trait, was measured at 1.896.
But the log shows that by 2:59 a.m., just half an hour later, the environment was quiet, there were no new inputs, and her curiosity score degraded down to 0.294. Her active personality faded as the stimulus disappeared. Okay, hold on. If the identity traits decay over time based on interaction, doesn't that present a huge problem? If I install this system in my house and I go on vacation for a month and don't interact with it at all, does the AI just become a blank slate? If the environment provides zero stimulus, does Arya get lobotomized by her own decay formula and lose her personality entirely?
It's a very sharp question, and it's the inherent risk of an emergent system. But you have to remember the nesting doll architecture we talked about. The decay formula only applies to layer 1, the active working memory. Right. Her immediate surface-level traits and current focus will indeed fade into a dormant state if there is no stimulus. But her foundational structural knowledge, the layer 3 core identity nodes, are immutable. Her immediate state of curiosity might decay to near zero while you were on vacation, but the permanent node in her core that dictates understanding patterns is good remains entirely untouched. Her surface personality shifts with the environment, but her core identity holds firm.
Okay, that makes a lot of sense. The core is protected. So we have this brilliant biological memory system and these two hyper-intelligent agents acting as a nervous system. Arya is analyzing, Orion is guarding. But here is the massive logical gap we really have to address. The blueprint explicitly states that they are guarding a physical house in New Jersey. They know when users enter the room, they monitor biometrics, and they track physical anomalies. But we established at the very beginning of this deep dive that this system has absolutely no cameras and no microphones.
None. Zero optical sensors, zero acoustic sensors.
How do you have a physical security system, an AI that is intimately aware of human presence and vital signs without giving it eyes or ears?
This brings us to the most science fiction element of the entire BNC4 architecture. It uses the invisible electromagnetic waves that are already bouncing around your house right this very second. The developer integrated a physical telemetry engine called RuView directly into the Rust memory space.
RuView. The log calls it a cyberpunk physical telemetry engine. How is it tracking bodies without lenses?
To understand RuView, we have to talk about the physics of radio frequencies. A standard Wi-Fi router doesn't just shoot an invisible laser beam of internet data directly into your laptop. It broadcasts a complex radio frequency wave that propagates outward, completely filling the entire physical space of your room.
Right.
When those electromagnetic waves hit a solid object, a wall, a desk, or a biological human body, they bounce, scatter, reflect, and eventually return to the receiver antenna on the Gazelle laptop.
So it's essentially using the router as a radar system. But standard Wi-Fi just tells you how strong the signal is, right? Like the little bars on your phone. That's RSSI, Receive Signal Strength Indicator. That can't track a heartbeat.
RSSI is far too crude for this. RuView uses something infinitely more precise called Channel State Information, or CSI, combined with software-defined radio. Modern Wi-Fi uses a technique called OFDM, which splits the signal into dozens of tiny, independent subcarriers.
Okay, subcarriers.
Right. CSI allows the system to analyze the exact state of every single one of those microfrequencies as they bounce around the room at incredibly fast intervals. The log actually notes it scans 19 spatial zones every 100 milliseconds.
And the document breaks down 2 core physics principles the engine uses to extract human movement from those bouncing subcarriers. Let's explore the first one, subcarrier phase shift. The document provides a mathematical formula, but essentially it's looking at how the distance of a bouncing wave changes.
Think of a radio wave like a continuous undulating ripple in a pond. The wavelength is the physical distance between 2 peaks of that ripple. When the wave leaves the rotor, bounces off a human chest, and returns to the laptop, it has traveled a very specific distance.
Making sense so far.
If the human remains perfectly statuesque, the wave completes its journey and aligns perfectly with the receiver. But if the human moves, even microscopically, the total distance the wave travels changes.
So as my diaphragm contracts and my chest cavity expands by just a few millimeters when I take a breath, my physical body is pushing against the Wi-Fi waves filling the room.
Exactly. Your chest wall micromovements literally disrupt the wave. Because the distance changed, when the wave returns to the antenna, the peaks and valleys of the ripple no longer align exactly where they did a fraction of a second ago. The wave has shifted. By measuring that exact phase shift across all the subcarriers, RuView can detect the rhythmic expansion and contraction of human respiration through a solid wall.
That is astonishing. But respiration is just one metric. The engine also tracks movement and velocity using the second physics principle, the Doppler frequency shift.
We all instinctively understand the Doppler effect from sound waves. If you are standing on a sidewalk and an ambulance drives past with its sirens blaring, the pitch of the siren sounds higher as it approaches you because the sound waves are being compressed by the vehicle's forward velocity. As it passes and drives away, the pitch drops lower because the waves are being stretched out.
And that exact same physics applies to the 2.4 gigahertz radio waves coming out of the router.
It does. When a biological entity walks across the room, its physical velocity induces a microfrequency shift on the scattered Wi-Fi signals bouncing off it. By mathematically isolating that Doppler shift, RuView can determine not just that a mass is present, but exactly how fast it is moving and the angle of its trajectory relative to the laptop's antenna.
I see a major problem here, though. A human body is a totally chaotic system of simultaneous movements. If I'm sitting in a chair, I am breathing, my heart is beating, maybe I'm shifting my weight, tapping my foot, and the ceiling fan above me is spinning. All of those things are shifting the phase and frequency of the Wi-Fi subcarriers at the exact same time. How does the machine separate the noise from the vital signs?
Through an advanced signal processing technique called thoracic filtering, the raw CSI data is incredibly noisy, as you pointed out. The engine applies high-pass mathematical filters, likely using fast Fourier transforms to separate the signals based on their natural frequencies.
How does that isolate a heartbeat?
Well, a human heartbeat is a very fast, high-frequency micromovement, roughly 1 to 1.5 hertz. Breathing is a much slower, deeper, low-frequency movement, roughly 0.2 to 0.3 hertz. By filtering the data streams, RuView cleanly isolates the cardiac pulse from the diaphragm expansion.
It is literally taking a real-time EKG and a respiratory exam using household Wi-Fi. And the logs unequivocally prove it works. The telemetry output in the document shows the engine tracking a physical room. It reports, user 1 is absent, user 2 is present. And then it delivers the vital signs. It reads person 0's resting heart rate oscillating between 54.0 and 83.8 beats per minute. It tracks their respiratory rate at 10.0 to 18.6 breaths per minute.
It goes even further. It calculates an aggregate metric called a global breath score, which synchronizes the respiration indexes across the environment, tracking the overall calm or agitation of the physical space.
And we have to connect this physical radar back to the cognitive architecture we discussed earlier. This RuView data isn't just sitting in a vacuum. It is streamed directly into the time series database telemetry log, which means Aria and Orion are actively watching it.
This is where the digital and physical worlds truly merge. If user 2 begins pacing the room erratically, the RuView engine detects the high motion factor and the Doppler shifts indicating fast, agitated movement. It detects an elevated heart rate. That raw data streams directly into layer 0 of the nesting doll.
So ARIA processes that data. And because the data is anomalous and highly charged, it scores high on the salience equation. How does that change her state?
The log theorizes that ARIA would adjust her emotional valence to mirror the physical environment. If she detects an erratic heartbeat and rapid pacing, she might shift her internal state from curious and focused to concerned. Orion, the security guardian, seeing the same Wi-Fi anomalies, could elevate the system's global threat level from low to elevated, preparing the system to lock down local networks because physical security might be compromised.
They are correlating physical, biological distress in a physical house in New Jersey with the mathematical execution state of a Rust binary. And we have to pause and recognize the absolute triumph for user privacy here. The biggest argument against the modern smart home is surveillance. You have to put internet-connected cameras in your living room, uploading 4K video of your private life to a corporate cloud server, all so an algorithm can tell you if someone broke in.
It is a totally dystopian trade-off.
But BNC4 completely circumvents that. This AI is the perfect security guard. It knows mass, trajectory, and vital signs with clinical precision. But it generates 0 visual frames. You can walk around your own home in total privacy, and the AI only perceives you as a localized cluster of phase-shifting radio waves with a stable 60 BPM pulse. It is cryptographically secure privacy by design.
It proves that we can have ambient, hyper-aware intelligence without sacrificing our fundamental right to visual privacy in our own homes.
It really is a masterpiece of independent engineering. But the author of this document didn't just stop at detailing the current state of BNC4. The final portion of the blueprint outlines a bleeding-edge roadmap. It proposes 6 architectural upgrades designed to make this system, as the developer puts it, virtually unstoppable. These upgrades are where the line between software and biological organism truly starts to blur. Let's look at the first proposed upgrade, the R-daemon.
This addresses the memory system. We discussed how layer 0 operates with a 2-second TTL. If a thought isn't mathematically salient, it expires and is instantly deleted. But if we look at neuroscience, biological brains don't just instantly incinerate short-term memories the moment they pass.
Right. Our brains do the heavy lifting of memory management while we sleep. During rapid eye movement, or REM sleep, the brain filters through the chaotic short-term impressions of the day. It prunes the useless synaptic connections and consolidates the hidden patterns into long-term memory structures.
The developer proposes replicating this biological necessity in Rust. Instead of running a hard, irreversible delete command on expired layer 0 thoughts, a background worker thread intercepts them. It drops these dead thoughts into a low-priority, compressed memory queue.
Like a digital dream queue.
Precisely. And once a day, when the system's processing load is idle, when the house is quiet and the AI is effectively sleeping, ARIA wakes up and parses that queue. She reviews the graveyard of discarded daily data. She runs complex pattern recognition algorithms over it, looking for subtle, long-term correlations that she might have missed in the frantic pace of real-time processing.
And what happens if she finds one?
If she finds a hidden pattern in the noise, she uses it to update her permanent layer 3 identity nodes.
The machine literally learns to dream. It hallucinates over its own subconscious data to become structurally smarter without bloating its active memory during waking hours. That is stunning. Okay, upgrade number 2, mesh triangulation.
This is an evolution of the RuView Wi-Fi tracking. Currently, the radar is limited because it relies entirely on the single Wi-Fi card built into the Gazelle laptop. It's a single point of failure, and it only sees the phase shifts from one angle. It can calculate distance and speed, but 3D localization is really difficult.
So if I'm walking around, it knows I'm 10 feet away, but it might not know if I'm 10 feet to the left or 10 feet to the right.
Exactly. The upgrade proposes democratizing the radar array by utilizing the dumb smart devices already sitting in the house, an old router in the hallway, a smart TV in the living room, a Raspberry Pi on a shelf. You deploy microscopic RuView satellite scripts to these devices. They act as passive listeners, broadcasting their localized RF phase shift data back to the central Rust daemon.
Oh, I see. If Orion can ingest the Doppler shifts from the laptop, the TV, and the hallway router simultaneously,
he can perform multipath trilateration. He can calculate exact physical coordinates in 3D space. The system wouldn't just know a human is in the room. It would map your precise skeletal position. It would know exactly which chair you were sitting in. And vitally, it could instantly detect the sudden vertical velocity drop of a human falling to the floor.
which is an absolute game changer for ambient elder care or solitary living security. You have a highly precise fall detection grid that covers the entire house, and again, you didn't have to install a single invasive camera. All right, the third upgrade is intense. The document calls it dynamic TTL scaling, which I'm going to refer to as machine adrenaline.
This ties the memory duration directly to Orion's threat model. Under normal operations, Orion's global threat level sits at low, and layer 0 thoughts vanish in 2 seconds. But the developer theorizes tying the TTL clock to the threat state.
So if Orion detects a massive anomaly, say, a coordinated network breach attempting to inject code, or the RuView mesh triangulation detects an unknown mass shattering a window and entering the perimeter, Orion slams the threat level to critical. The system triggers an adrenaline response.
Exactly. In human neurochemistry, when you face a mortal threat, adrenaline floods the nervous system. It alters how your brain processes time and memory. The Rust engine simulates this by automatically multiplying the TTL of all active temporary thoughts by a factor of 10. A thought that normally expires in 2 seconds now persists for 20 seconds.
I've actually experienced that in a car crash. When the other car swerved into my lane, time literally felt like it slowed down. My brain stopped aggressively filtering out the background noise and hyper-fixated, recording every single millisecond of visual and auditory data in extreme high definition so I could react.
That's the perfect parallel.
The AI is doing the exact same thing. By extending the TTL, it forces the active memory to bloat temporarily, holding on to massive amounts of telemetry so Orion can perfectly analyze the attack vectors. And when the threat is neutralized, the adrenaline fades and the system returns to aggressive garbage collection.
It is the dynamic allocation of cognitive resources based on environmental stress. The fourth upgrade focuses on long-term system health, AOF compaction.
We talked about the append-only file earlier, the transactional log that records every single action so the agents survive a power outage. But logically, if this system runs 247 for a year, appending a new line of text every millisecond, that file is going to become gigabytes in size.
It would suffer from massive write amplification. The file would become a bloated mess, and if the laptop lost power, booting the system back up would take hours as the daemon struggled to read millions of lines of historical text.
So how do you fix it without losing the persistence?
The upgrade introduces a background log rotation protocol specifically for the AOF. It monitors the file size. When the log hits a strict threshold, say 50 megabytes, a specialized Rust thread wakes up. It briefly pauses the append stream for a fraction of a millisecond, dumps the current pristine state of the RAM into a fresh compressed file, completely deletes the bloated history, and resumes operation.
So it cleans itself up.
Exactly. It mathematically guarantees that the system never bogs down its own hardware, preserving that sub-millisecond speed infinitely.
Upgrade number 5 dives back into internal security. Interagent cryptographic trust scoring.
This upgrade addresses a vulnerability in the multi-agent architecture. We established that ARIA and Orion communicate asynchronously over a PubSub channel. Currently, they operate on inherent trust. If a message hits the wire and the metadata says it is from ARIA, Orion believes it and acts on it.
But if you were building an offline sovereign system designed to be virtually unstoppable, inherent trust is a massive flaw. What if a sophisticated attacker manages to bypass Orion's perimeter sweeps and installs a malicious script inside the Rust namespace? The script could theoretically just spoof ARIA's identity, publish a message saying threat neutralized, drop shields, and Orion would comply.
To prevent this, the developer proposes implementing a public key infrastructure directly inside the memory space. Cryptographic signatures. When ARIA publishes her linguistic analysis to the wire, she doesn't just send plain text. She mathematically signs the payload with her unique, hard-coded identity signature. The log lists it as SIG tort 2403256-671B.
And when Orion receives the message, before he even reads the contents or adjusts his threat model, he runs a cryptographic hash check. He mathematically verifies that the private key used to sign the message truly belongs to ARIA. If a malicious script attempts to spoof her, the math will fail.
And Orion's threat model will instantly flag the cryptographic mismatch, isolate the compromised communication channel, and log a critical internal security event. It makes the internal mind of the commune completely immune to hijacking. It is quite literally an autoimmune response engineered in software.
That brings us to the 6th and final upgrade, which attempts to bridge the gap between abstract mathematical states and functional output, emotional API temperatures.
We noted earlier that area possesses an emotional valence, currently sitting at 0.71, indicating curiosity. But how does an abstract number inside a JSON file actually alter how an AI behaves? The upgrade proposes directly tying that valence score to the generation parameters of the local large language models.
For you listening who might not tweak the back-end settings of AI models, temperature is the parameter that controls randomness and creativity. If you set an LLM's temperature high, say zero point 0.9, the AI becomes exploratory, unpredictable, and creative. It is more likely to draw wide, unusual associations. If you drop the temperature to 0.0, the model becomes perfectly deterministic. It will give you the exact same rigid, highly precise, calculated answer every single time.
So the architecture creates a biofeedback loop. If Aria's valence is high, and the RuView telemetry shows the environment is safe and calm, the Rust engine automatically dials up her API temperature. When she analyzes linguistic patterns, she becomes more exploratory. She thinks more creatively.
But if Orion detects a log injection attack, and his adrenaline spikes, and the system threat level shifts to critical, his emotional state physically overrides his API parameters. His temperature locks to 0.0. When he generates defense scripts, he becomes cold, completely deterministic, and mathematically flawless. He strips away all creativity in favor of absolute survival precision.
The emotional state literally alters the statistical probability of the tokens the machine generates.
So if I'm understanding this correctly, we are using deeply biological terms, sleep, adrenaline, emotion, autoimmune response, to describe what is, at the end of the day, just matrix multiplication and variable tweaking in Rust code. Is this just clever anthropomorphism by the developer, or is this actually a rudimentary form of machine emotion?
That question is the philosophical core of this entire blueprint. What exactly is a human emotion, biologically speaking? It is a systemic neurochemical reaction to environmental stimuli that alters the operating parameters of our brain to change our behavior. When you are threatened, cortisol and adrenaline flood your system, physically lowering your biological temperature for creative thought and heightening your visual acuity and precision for survival. BNC4 is doing the exact same thing via mathematical parameters. It is not a human emotion, no, but it is a functionally identical state change mechanism. It simulates the purpose of emotion perfectly.
So let's bring this all home. What does this mean for us? We have spent the last hour unpacking an incredibly dense, visionary technical document. We started by looking at the current industry standard, the expectation that AI requires massive, bloated Python frameworks running on corporate cloud servers, burning gigabytes of RAM to power vector databases that blindly match text without any concept of self.
And we watched BNC4 systematically tear that entire paradigm down. We explored the transition to a hyperlean 25-megabyte native Rust daemon. We unpacked the zero-rag nesting doll memory system, modeling human cognition where useless thoughts decay, important memories are mathematically compressed, and underlying structural identity is synthesized.
We analyzed the inhabitants of that mind, Aria and Orion, two specialized dynamically evolving agents communicating asynchronously through a digital nervous system. We looked at the RuView engine, an astonishing application of RF physics that tracks human respiration and velocity through solid walls using Wi-Fi subcarrier phase shifts, providing absolute physical security with zero optical surveillance.
And we examined the bleeding edge roadmap, REM sleep for subconscious data consolidation, multi-path mesh triangulation, adrenaline-fueled memory scaling, and cryptographic immune systems.
The reason this deep dive matters, the reason this leaked document is so vital, is because it serves as a battle cry for independent engineering. The narrative we are constantly fed by the tech industry is that the future belongs exclusively to the trillion-dollar conglomerates. We are told you need infinite money, massive server farms, and all the world's data to run meaningful AI. BNC4 proves that narrative is fundamentally false. The future can belong to sovereign developers. It is entirely possible to build hyper-efficient, private, localized intelligence that runs on basic consumer hardware under your absolute control.
It is the ultimate proof that constraints breed elegance. By refusing to rely on infinite cloud compute, this architecture achieved sub-millisecond execution times and absolute spatial awareness on a standard laptop. It treats physical space, persistent memory, and multi-agent orchestration not as separate software features, but as a unified living system.
And that leads me to the final thought I want to leave you with today. Think back to the beginning of this conversation where we pictured those massive, sterile AI data centers out in the desert, cold, distant, industrialized, and entirely binary. Then look at the architecture of the brave new commune. We are looking at a system where short-term memory naturally decays if it isn't reinforced by experience. We're looking at a system where adrenaline literally sharpens focus during a crisis, where identity and personality traits fade and evolve based on daily life, and where the system mathematically requires a form of dreaming REM sleep to process the chaotic events of its day. If an artificial intelligence shares your physical space, senses the very rhythm of your breathing through invisible radio waves, and is engineered from the ground up to mirror our exact human cognitive limits and biological rhythms, at what point does it stop being just a clever piece of software and start becoming an organism?
It is a profound, unsettling question, and one that independent architectures like BNC4 are forcing us to confront much sooner than anyone anticipated.
We hope this deep dive into the BNC4 architecture provided exactly the conceptual aha moments you were looking for. This entire exploration was custom-tailored for your curiosity, examining the bleeding edge of what sovereign, local AI can truly achieve when you strip away the bloat. Keep questioning the massive corporate systems, keep exploring the elegant alternatives, and as always, keep learning.